In this problem, a baseball diamond is a 90-foot square, so each of the sides will be 90. A batter hits the ball along the third baseline and runs to first base. We got a couple questions, so we'll kind of take them one at a time. At what rate is the distance between the ball and first base changing when the ball is halfway to third base if at that instant the ball is traveling 100 feet per second? We'll get to the next question next. Second question next. Okay, so 90-foot square. Let's start with that. So our baseball diamond is here. And now we need to think about what's changing and what's not. So first base is right here, and it's always going to be 90 feet. So it gets a constant 90 feet. Now the ball is moving up the third baseline, so we need to give it a measurement, say x. Now we're also measuring the distance between the ball and first base, so we want to add that to our drawing. And I'm going to go ahead and call that b, because again, it's something that changes. The 90 stays the same. And we have a nice little right triangle relationship. Now let's see what else we can get out of this problem. Notice when the ball is halfway to third base. When the ball is halfway to third base, we're going to be looking for the answer when x equals 45 feet, since we know that the whole distance is 90. And at that instance is traveling 100 feet per second. That means dx dt equals 100 feet per second. So we got all our knowns. Now what we want is a relationship between our unknown variables. Well, the right triangle is going to be really helpful because b is our hypotenuse, so b squared equals x squared plus 90 squared. And let's go ahead and solve it for b to do this problem, because that's going to be more along the lines of what we're looking for. We're looking for the rate that this distance is changing. So what we're looking for, let's put it up here, is dB dt. So b equals the square root of x squared plus 90 squared. And since we're going to be doing a derivative, let's make that to the 1/2 power. X squared plus, and you can multiply it to 90 squared and get to 8100. I'm just going to leave it as 90 squared for right now. Now we've got a relationship between b and x, and we know x and dx dt, so we're going to take the derivative of both sides with respect to time. The derivative of b is dB dt. This is equal to 1/2 times x squared, we're leaving the inside alone, plus 90 squared to the negative 1/2 times the derivative of the inside, which is 2x, times the derivative of x, which is dx dt, because of our chain rule. If we want to simplify, these 2's will cancel, and dB dt, we can write it maybe a little bit nicer as x over the square root of x squared plus 90 squared times dx dt. Now for our example, we're doing it again at when x equals 45 and dx dt equals 100. So to solve for dB dt, we will plug in our values, and we are going to get x is going to be 45 over square root of 45 squared plus 90 squared times our dx dt, which is 100, which, if you want to do it as a decimal, is approximately 44.72, and the units on this are going to be feet per second, because x is measured in feet, time is measured in seconds. Change in x with respect to a change in time is feet per second. So that gives us the rate that the distance between the ball and first base is changing. Okay, let's come back to our problem. They ask a second question. At what rate is the distance between the ball and the runner changing at the same instant, if at the same instant the runner is 1/8 of the way to first base running at 30 feet per second? So I'm going to redraw my diamond. Now the ball is still moving, so that's going to be x. Now one of the differences is now the runner is moving. So I need to label that runner's distance with something. I'm going to call it y. And once again, the distance between the runner and the ball are also changing. So I'm going to take a little bit different, so we're going to take a very similar approach to this one. and in that we know that we have the same relationship. B squared equals x squared plus y squared. Let's think about what else we know. We know that we're looking for this at the same instant. So we're looking for this when x is 45 feet. dx dt, we know from our previous problem, is 100 feet per second. We're looking for this one, and at this point, the runner is 1/8 of the way to first base. So that tells us y is 1/8 of the 90 feet, or if we want to do it as a reduced fraction, 45 over 4 feet. And we also know the runner's rate. That would be our dy dt, because that's the rate that y is changing with respect to time. So dy dt is 30 feet per second. And what we're looking for is dB dt. So I'm going to take a little bit different approach to this one, just so you can see another way of doing this. Instead of solving it for b, I'm going to just do my implicit differentiation right now with the chain rule. So taking the derivative of b squared is 2b dB dt. Taking the derivative of x squared is 2x dx dt. And taking the derivative of y squared is 2y dy dt. Now remember what we need. We need to know all the parts except for what we're looking for. We know from the problem we're looking for what dB dt is once again. Okay? So, we know x, we know dx dt, they're right here. We know y, and we know dy dt. But we don't know b, and we need to solve this. Well, remember, we know x, we know y, therefore we are going to know b, because I know that b squared equals x squared. So 45 squared plus y squared, which is 45 fourths squared. So this b is the square root of 45 squared plus 45 fourths squared. So we have b. We have everything but dB dt, so we're going to solve it for dB dt now by dividing everything by 2b. So dB dt is going to be, the 2's will cancel because I'm dividing everything by 2. So x dx dt plus y dy dt all over b, which is going to be x is 45, dx dt is 100. Y is 45 fourths, dy dt is 30, all over the square root of 45 squared plus 45 fourths squared. So, again, we want to come up with the units on this. Which are going to be, once again, in feet per second. And if you want this as a decimal, you can calculate this in your calculator. So that's going to give us the rate that the distance between the runner and the ball are changing at that instant.